and it is clubbed with his 85th birthday. So the colloquium will be followed by a short felicitation, and then we'll have a lot of talks. The topic of this extended discussion meeting would be simulations in chemistry and biology. But we are going to start with an institute colloquium by Professor Klein, and I would like to invite. I would like to say Professor Klein is a N.R. Kamath Chair Professor. It's a very prestigious chair in our in IIT Bombay, and Professor Devang Khakkar from Chemical Engineering and Professor Murgavil are the two lead proposers. And what I want to say really in a nutshell is it's both chemistry and chemical engineering. Anyway, science doesn't have boundaries. I want to say that again and again. But it is both chemistry and chemical engineering putting together as a concerted effort here to have Professor Klein with us at IIT Bombay. With that, I will invite now. I also want to say Professor Wagmare from JNCSR, who's with us in the audience. And I thought it over a dinner with Mike, and we just said we should do this and have the community come together. So we have a lot of speakers from across India who are coming. Some of them are students of Professor Klein who are here. So with that, I'm going to invite Professor Murgavil to speak a little bit about Professor Klein.
Thanks, Ruchi. I happen to see Professor Mike Klein more often than many of my colleagues in the department, actually. It's only 4 weeks back I met him in Bangalore, and 4 weeks later we are here together. I've known him for a while, maybe 20 plus years, but maybe even before that. I think Bala is in the audience. Where's Bala? Yeah. Bala left for Philadelphia and me to Germany almost the same time. And he was sitting in Mike's lab, and I was sitting somewhere else in Germany, and we used to communicate, I think that's the first time I got to know about him. But then maybe I'd known him, one-to-one for 20 plus years. But the one thing I want to recall first before I read this long CV is me pouring a glass of wine on your shirt not long ago in Trivandrum during a dinner. So that's where probably you got to know much, much better each other. Okay. Professor Klein, he is a Laura Cornell Professor of Science at Temple University currently, where he is also the Dean of College of Science and Technology. For those who do not, hardly there will be anyone in this audience who does not know Mike Klein, but let's still give a brief introduction. He was born in London, grew up in England, did all his bachelor's, master's, and doctoral studies in UK before moving to Italy, where he spent a short period in Genoa. Am I right, Mike? In Genoa. And then from there he moved to Canada, where he's actually spent quite a few years with the NRC, National Research Council of Canada. And in '87, from NRC he moved to University of Pennsylvania and stayed there till 2009. That's about 22 years. In University of Pennsylvania, Philadelphia. I think there he formally kind of superannuated and only moved a few blocks away from UPenn to Temple, and he has held various positions both at UPenn and in Temple all these years. And he gave me a brief CV 2 years back, which I just actually holding in my hand. And a lot of things have happened in these last 2 years. I want to talk about last February he was here in IIT Bombay. From here he traveled to RAK, Rasselheim, where he was awarded the very prestigious Sheikh Saud International Prize for Material Science. And he has been a fellow of the Royal Society, elected long ago, fellow of the National Academy of Sciences, fellow of the Trinity College, Cambridge, Debye Award in Physical Chemistry, and he's also Anizir Award of the American Physical Society. The list goes on and on. Just to kind of summarize everything in just a couple of sentences, his area in computational chemistry and computational biology has been published in over 1,250 journal papers. That itself is a big number, and you will be more astonished to know that these papers have been cited some 130,000 times, or 130,000 times, And of which, one paper what he published in 1983 in JCP alone has been cited 43,000 times. One single paper, 43,000 times. And in 2024, that paper was cited 3,000 times. And I was just looking up this morning only as Ruchi was giving a presentation. Normally, when you publish a good paper in a very competitive area, the first 5-6 years are all cited well, then it will kind of go down, okay? And this paper has been going up. Mike, I don't know what's the reason. I mean, like 83 of 42 years, since this paper was published, the citations are only getting, better and better every year, okay? I can go on reading this, but I'm not going to do this because we have only 45 minutes to present what you're going to talk to us. With this, let me call Professor Klein to present his lecture on water and water everywhere. By the way, that paper, 1983 paper, I will read the title, Potential Functions for Simulating Liquid Water. That's the one which is having 43,000 citations. Mike.
So, good afternoon, everybody. Can everybody hear me okay? Good, good, good. It's a pleasure to be here. I was here last year, and great to be back. I picked a very general topic for today, just water generically, because I thought there would be a general audience, so we'll see how it goes. So, as Maruk's mentioned, I was born in the UK, and my relationship and fascination with water is pretty complicated. So, I grew up in a very modest house in London, that working class neighborhood, that didn't have an inside toilet and it didn't have a bathroom. So, for multiple reasons, bath time was to be avoided at all costs. And the idea of stripping naked in the English climate was abhorrent. And even more so because it would be in the backyard and I would have to get into a tin tub and have buckets of water poured over me. And for most of the year you would shiver. So I think this is the origin of why the Brits in general have an aversion to water. So my attitude changed when I was a teenager and visited the south of France and understood that going to the beach and lolling around on the sand could be fun. Whereas in England, it was freezing cold with the north wind and you shivered to death and people were supposed to pretend they enjoyed it. Anyway, the visit to the Mediterranean changed my view. And as I said, the modern day today, I still have an aversion to getting into a bathtub. I can take a shower, that's different. But my fascination for being by the ocean is lasted at least 7 years. So let me get into the talk. So this iconic picture taken by astronauts from Apollo 8 is probably one of the most iconic photographs ever taken. It taught us all that our world of Earth was finite. And I think most people, if you go through the centuries, argued about whether the world was round or flat. But this taught us that we were really just one ecosystem. So very, very powerful image. So here's Earth with satellites, and we monitor more or less every day what's going on. Lots of people do. But as I said, I'm fascinated by water. So here's a picture of the part of the world where we are now. It's India under the clouds. And I put an arrow to a little island in the Mediterranean that I visited a few times, especially recently. And I was there to celebrate my 80th birthday. And this is the view in Eritrea. You're at about 1,000 meters altitude looking down on the Mediterranean. Another interesting view of Earth, when I leave Bombay, I'm going to be going to Dubai and to Ras Al Khaimah, and one of the deep attractors of Ras Al Khaimah is the view of the water again. And I said I'm kind of obsessed with seawater, so this is the sun setting in Ras Al Khaimah. Actually, the view is from a hotel that we had the meeting at last year. This is the hotel in the distance, built so that the two buildings aligned with the setting sun. So this was, I jumped to, so I just left the 2-day journey to get here. And in case you think I just live by the seaside, this was the view looking through the window when I left Philadelphia. So it's a pleasure to be here. And you can see there was even ice crystals growing on the window. And so that's what I left behind in Pennsylvania. So let's move to another part of the US where I visit quite often is in Florida, where I have a second home. And this is, again, my obsession with being by the ocean. This is sunrise in Florida, looking east over the Atlantic for sunrise. So once the sun is up, this is what it looks like. It's very idyllic, and it's sufficiently peaceful that turtles nest on the beach here. So we get the pleasure of watching that recurrence of nature. The same view, when it happened to be raining, about 5 kilometers offshore where the Gulf Stream is, high humidity there, high temperature and raining. But the sun is now behind, and so you see a rainbow, even though you're looking there. Rather unusual view. If we look the other way, we have a setting sun, and after the sun sets, we get this. So perhaps these few images explain my fascination with the sea and sea water. But it doesn't end there. If you have the sun setting behind you, and you look eastward over the ocean, you can see the moon rising. And here's a picture from my house in Florida looking at the moon rising. But what happens when the moon sets? The moon sets, it depends on the time of the year, the moon sets when the sun is rising over the ocean. This is an image I took of the moon setting. Would you guess that? Most people would think that's the sun, right? Am I the only one? You're surprised? I happened to look out the window and I thought, this is wrong. It can't be, but it's actually the moon setting. All right, so enough of my amusement of being by the ocean. According to a government website in the US, 71% of the planet is covered with water, the surface. That would seem to be rather a lot, but unfortunately most of that is salt water. So how much water is there actually on Earth? I was surprised in preparing these slides at how small it is. So this is an image that I took by going back to the literature. In fact, if you took all the water on Earth and you made it into a sphere, that's the size of the amount of water on Earth compared with Earth. Did everybody here know that? Are you surprised? Who's surprised? Yeah, I thought that was an interesting fact, right? Now, unfortunately, the amount of pure water everywhere is the tiny little sphere. So this is fresh water, and the amount of water in lakes and rivers is the even smaller sphere that you perhaps cannot see. How many people realize that? So the amount of water is in this table. 96.5% is salt water. You have buried in ice and snow, 1.7%, and in groundwater, only 1.7% of the water. So this is why we need chemical engineers to build good separation plants, efficient ones, okay? So 3 cheers for chemical engineers. And you can see that some of the others are infinitesimal. I must say I was incredibly surprised by this. I mean, obviously I knew fresh water was small, but I didn't realize how small. Okay, many books have been written about water, and some of them recently. I even bought a couple of them just to see what they had to say. Philip Ball, who was an editor of Nature for 20 years, writes popular books, and he wrote a book on water. And in fact, he published essentially the same book a couple of years later with a different title. Maybe the first one didn't sell. The title, as we know, is important. So this was called A Biography of Water. The second one had a different title, and Life's Matrix. So I'm not encouraging you to buy these books. I'm just saying that I did, just in preparing this. I must say I personally didn't learn anything new. However, we have somebody else here that who's written a book on water. I would say for those of us that are scientifically oriented, this is a much more useful book than the popular book by Philip Ball. So Beeman might show up, right? Beeman's not here at the moment. Oh, there's Beeman. So why don't you stand up? So here's Beeman. As I said, much more useful book. So I posed a question. So water's everywhere, and I've just explained to you it's all salt water, whether we like it or not. But where did it come from? And was it always here? People know? I must say that I was surprised to find out that we still are not sure where it came from, although we are getting closer to understanding. So this paper caught my attention. It's already 10, 11 years ago. And this paper came up with the conclusion that underground, 500 kilometers down, there's at least as much, if not more, water than there is on the surface. So I don't know if that's going to be useful in the future for the survival of the planet, but anyway, it's there. And there was an astonishing finding that as you go down, of course, the temperature and pressure go up. And the common minerals, there's a lot of magnesium ion silicates as you go down into the earth. And there's a phase transition in structure occurs. And there are two forms. This is the more familiar to chemists, I think, whereas this ringwoodite was a somewhat new material that was identified in these studies. So there was a popular article written about this discovery, and so the more usual mineral would have been olivine, and it makes a transition to ringwoodite. Now, it turns out that ringwoodite was identified in the 1960s as a mineral that was discovered on a meteorite. And the meteorite came from, of course, outer space. So how did that get there? How was it formed? But I already alluded to the fact that this particular mineral is unusual in that it accommodates OH minus, not water in its usual form, but something that could react to form water rather easily. So the interest in this paper, if you go back and read it, is this particular meteorite landed in a desert part of Australia. So it's argued that, in fact, it didn't undergo any weathering of any substantial kind, and that it's pretty much as it was when it landed on Earth. So they're pretty confident that this mineral is out there in space. Same year in Nature, a paper came out and said, Earth's water is older than our sun. So that's fascinating. Fascinating observation. And how did people come to this conclusion? And it's by studying the hydrogen-deuterium ratio. They can show that there are differences between the water that comes from space on meteorites or comets is different from the water in our oceans. The conclusion from this paper was that at least a third to a half of the water arrived later. So the sun didn't wipe out all the water in the interstellar cloud from which the sun formed and created our little system. So that's not the end of the story. This is just another article that came out, which was discussing somewhat similar themes. That where did the water come from? Was it formed at the time of our little system was formed? Or in fact, did it come from outer space, from the nebula? The nearest nebula to us is Orion. So the conclusion from this particular paper was that if what we have on Earth is typical of formation of planets from the sun and then the planets around it, then this phenomenon that we have here on Earth must be common. It should be possible in other suns of forming. So I never read these papers 10 years ago, and I was pleased that I found them. And in the universe that I move in, nobody had ever talked to me about these papers. So I think they're rather profound, especially if you have any interest in the origin of life. How did life come to be on Earth? Well, these are not the only papers. A few years later, this paper came out from a group in Germany. And their conclusion is here, that the late delivery of some of the water on Earth probably occurred with some disruption in our system of planets, particularly with some of the large giant gas planets further out. And this again was done with essentially analytical chemistry tools, looking at isotope fractions, in this case, studying molybdenum. But one thing that came out of this for me, not being an astronomer, is that the consensus view at the moment is that the moon was formed by a collision with Earth with another huge object. And this caused the formation of the mass that formed the moon, so that much of the moon should look like Earth, the minerals in it. And it turns out that the structures involved are very similar to the meteorites that typically land on Earth. So there's a little bit of controversy here as to whether this also brought some water. Remember what I was saying, that if we go down a few hundred kilometers, you have minerals that could in fact generate water. So this collision may have in fact also generated some of the water on Earth. So then this paper came out relatively recently. This one I noticed in 2020. It's again to do with isotope ratios, H to D. This is a group in Nancy, France, 2020, published this paper. They reanalyzed these isotopic ratios in a bunch of meteorites 13 of them, in fact. And it says here that what they claim to show, they say that most of the water would have been delivered by meteorites to Earth. I think this was a little controversial, but that was their conclusion. That's how it was published in Science. And this article was considered sufficiently interesting that there was a commentary on the article in Science by somebody from NASA. And so this cartoon attempts to summarize where we are with our understanding of how water came to Earth. So there are essentially three. These are these meteorites I've been talking about, that they could have come from the structure of these minerals that contain water. And the last thing is that it could have been delivered by comets. So the issue is whether the ice is delivered as water, or it came in as ice, sorry. It can come in. If it comes from a long way away, it might actually bring ice crystals with it. So those of you, I don't think there's a lot that's happened since this paper. So it says here, combining these data, they show that most of Earth's water could have come from meteorites. What does most mean? Does it mean half, which was the earlier estimate? So I don't think it is in contradiction with what came before, but it reinforces the fact that some of the water was here when planet Earth was created, and some of it, up to half probably, came after the planet was formed. So I don't think there's any new information on this article, but this is relatively recent, 2023. Where did it come from? The conclusion here is that there are two essential sources. It was born with it, or precursors of it, as I said, in minerals, or it came from outside. Could be multiple sources. So I think that's pretty up to date where we are. However, there's some more modern stuff is going on. So when a sun is formed by gravitational forces bringing together lots of pieces, and they form, you form a sun, and there's still around this sun some debris that forms a disk, and then other things like planets can nucleate out of this disk of material. So astronomers have been interested in going out into the universe and looking for new suns that are forming, and to try and get some clues. What do you find in these primitive solar systems? So this is a paper that caught my attention. This one comes to the conclusion that the recycling of what goes on, equivalent of Earth's oceans of water, which essentially means all the water on Earth, is destroyed and replenished every month. And this has consequences in affecting the hydrogen-deuterium ratio, basically. And they claim that this explains why the deuterium fraction of Earth's oceans is different from what you find in space. So this is a very recent paper. I don't think there's been enough time for the people with the other view that half of the water was here and half has come later, but this is the fact that OH was detected in a planet-forming disk. So what is the disk that they studied? I thought I'd take a couple of minutes to explain. So two important telescopes are out there, and this one is from the new telescope, the James Webb. And what they did is they're going in, this is Orion, the cluster of stars, the hunter with the belt here. Here is where Orion is. So they go and look at these telescopes, which are phenomenal objects. Here's a photograph of looking into Orion. And this is referring to the thing I saw before. When they looked into Orion, they found OH. They detected OH. So that's important because that brings up issues which have been around for 100 years plus, where people, what is the origin of life? And there's some very early works which those of you who are interested should go back and look at. These articles by very original people and very influential. So let's go into a tiny bit more detail about the Orion Nebula. In the Orion Nebula, there are lots of really stars here. There's a group of 4 referred to as M42. The original image is here, so I've tried to give you a clearer image of this core here in the Orion Nebula. So that's where they're looking. And they can image this with different wavelengths. And this is, again, we're looking at the same place. And I'm going to focus in on an area here. And here you've got 2 dots, if you look closely. I've expanded that square over here. You can see 2 dots. And it's this one we want to focus on here. And this is the sun forming with its disk of matter around it. So that's where they're looking. And in the most recent works that have come out, they've detected CH3+. So not only have they found OH out there, they found CH3+. So this is exciting for people that worry about the origin of life, because this is a solar system forming. It's got nothing to do with Earth, but you have the elements that you need to give us life. So that's pretty much where we are. Topical issue of PNAS just came out literally a couple of weeks back, 3 weeks ago. And this particular issue is full of articles about going into search on the moon and Mars for water. And as I said, because it's believed that moon was formed by collision of another object with Earth, it should have, at least underground, water, if not in other areas of the planet, of the moon. So I'm not going to go into these articles. They're all about the future and what these missions will be and what will the instruments be to do that. So anyway, that's where we are, and I thought you might be interested to know a little bit about where water come from. And as I said in my abstract, that I don't give any new insights as to where it came from. But if you're like me, you had no idea. Did you ever ask or thought about where did the water come from? So that's the end of my formal lecture, and be happy to take questions. Yeah. Yeah, I'd be happy to if people have questions.
What is the basis for saying that water could be older than the sun?
So it's based on the hydrogen-deuterium ratio. What we find if we look at water, be the same in your tap water, that has a few percent deuterium. And when you look at ice that's been brought, eventually water, or inclusions in meteorites, the hydrogen-deuterium ratio is different. And so the conclusion from that is that the water was essentially in the disk from which our sun and planet nucleated and the system was created. So what comes in with meteorites or comets now is a different isotopic ratio from the water here. Since the dominant water here is the ocean, I said 97%.
Yes.
The conclusion is that it's there in the universe. So the extrapolation from that in the paper is that the probability of creating a planet like Earth, Earth-like, that it will have water is finite. But if you want me to defend the analytical chemistry, I'm not an analytical chemist, but I just toss that out, okay?
Thank you.
I have a question, Mike. Actually, it's more philosophical. If water is there in the nebula, why is there so difficult to find life? Because water is one of the, at least when we look out, we send out things. It's not like, we hit life easily. So if water is present, you can detect. Why is it so difficult to have such large amount of it? Because I think that's important for life. What's going on there? I just wanted some thoughts.
So I don't quite understand. You're saying, why is there so much water?
No, why life is so difficult to find when water you can find in different places? If water may be one of the catalyst for life, I would assume.
Well, there
Some
are
kind of life.
a myriad reasons why you might not have life. So when these planetary systems are forming, they're not in total isolation. There are nearby stars. I showed you in the nebula, you have these 4 suns forming what they call the trapezoid. It's a trapezoidal structure. The radiation from these as they collapse and go to form the sun is so enormous, you would have radiation damage. So you're creating this object in an intense field of radiation. And so you would have to wait.
Wherever we are looking in those places.
Yes, right? They're looking, but this evolution is going to be billion years or more, the age of this. I mean, it's the notion that we would find it by looking for a few years is
not going to happen.
Is a bit naive, yes. But what they've shown, these recent papers, we have the elements, the basic elements.
Mike, this 50%, your estimate, kind of approximation,
Yeah.
50% was here in some mineral form.
Yes.
Now, this Jules Verne's journey to the center of the earth. There was this huge water.
Yes.
And there's a river. Now, that was very interesting, that thought. But now, if in form of minerals, and you presume that some kind of collision, some chemical transformation made into water. And that is, I'm difficult in imagining. And second, how would then come, in Jules Verne's novel, at least water stayed inside. How does it come on surface?
Well, so the idea goes back to the original collision with formation. Mm-hmm. So, as I said, the consensus view is that the moon was formed by a collision.
At the time of
that massive collision.
Yeah, that was at the time of the formation of the planet or moon. Then, rest 50% approximately comes with the meteorites.
Yes. Yeah. That's the consensus view right now.
Thank you. Because I'm writing this book where I put all credit to meteorites.
Well, in fact, the very fact that you sent me that book caused me to write this lecture.
Thank you. Mm-hmm.
Thank you.
Thank you.
I thought it would just be useful.
Great, because I got a lot of material.
Okay.
Thank you.
So, relating to Ruchi's comment or question, Mike, there are 2 recent discoveries. One is based on the James Webb Telescope, where in nebulas they have found small carbon-based molecules, which are a good sign of life possible. But as you said, it will take billions of years to evolve that into life form.
Yes.
And the second one was, of course, the asteroids bring lots of organic molecules to the Earth as well.
Yes, that's another issue.
Observation.
Indeed.
Yeah, that's right.
And then these famous experiments that were done, where you put the simple gases in a tube and you put voltage through it, electric field, and you find primitive molecules, including amino acids. So, but that assumes that you have an atmosphere.
Yeah, that's right.
So that's way on, right? So you form your planet, you have some water, but now you're assuming you also have methane, but this seems reasonable now. But do you have ammonia? So there are lots of hints there.
Sure.
And then the issue is not only you make an amino acid, how do they then polymerize? Okay, so there are lots of papers on it. In fact, I have a paper that's out there on the archive right now. And it's very important, if we were right, to have a mineral surface which will orient the peptides so that they're ready to polymerize. So by 10 orders of magnitude more than gas phase collisions. So the minerals, we know were there. It's an evolving story, but it's a fascinating one.
Thank you very much. I really enjoyed your talk. You said that there's somehow water is stored in minerals, and that was very interesting to me. Do you know what the driving force is for sort of the water or oxygen, hydrogen stored in to come out? Is it temperature, pressure?
Oh, so yes, so there's no reason for it to come out spontaneously, right? So that's absolutely correct. In this form of the mineral, which goes from the perovskite structure to this other structure, you have a lot of defects in that structure where O2 minus, so if you've got MgO, you've got 2 plus and O2 minus, you have, instead of O2 minus, it's site substituted with 2 OH minus. And that's at a 1% level. That's how they come up with this estimate of just the same amount of water. Now, how does it convert? Good question. But if you read the details of the paper that I showed, the importance of water there, they're arguing, is how the tectonic plates move. It's a kind of lubricant. So as the plates move, geological timescales, they're actually releasing some water. Not on the scale that makes the oceans. It's just an observation that down there we have. So it then asks back to the question, as we got earlier, when this was formed by a collision, when the moon got kicked off, did that produce a lot of water? It's a question rather than a fact. Okay.
Very nice talk, sir. So recently scientists has discovered like polar ice caps on Mars, and one of the Jupiter's moon, Titan, has ice caps and water in it. So are they similar water as in Earth, like the distribution of this deuterium and hydrogen ratio? They're the same, or they are coming from different things?
I didn't, just because shortness of time, I didn't talk about modeling water, but it's more than 30 years ago I wrote a paper as to what happens to ice if you compress it on a computer to the conditions that might be appropriate for the giant planets like Uranus out there, the big giant planets. Our paper came to the conclusion that water wouldn't be water. It would be completely ionized. It would be a lattice of O2 minus, and the protons would be like electrons going through it. So this paper was published, I think, 1988. 30 years on, 2018, there was a paper in Science that confirmed my prediction 30 years later. So it's another example in science. You need good genes if you're a theoretician. So yes, there are many forms of water out there, and the reason I did that calculation, I was talking to people that were doing experiments with diamond anvil cells. And it seemed to me, well, maybe at some day they're going to be able to make billions of atmospheres pressure. High temperature is a different thing, but what would ice look like? And actually, when the experiment came out, I got a note from Professor Parinello saying, Mike, you made some lucky approximations. I wrote back, no, that's called intuition, Michele. so yes, many years later, Michele repeated what we did with ab initio molecular dynamics.
Yeah, it's getting close to 3, so let's thank Professor Klein for such a fascinating lecture on water. May now request Professor Kakkar to hand over a small memento.
Should I come down?
I think for camera it's better to do that he goes up.
Okay.
Yeah. You have flowers?
Okay.
Great talk.
different. It was a gentle talk. Thank you.
Yeah, that's from us and this from the Institute PRO.
Okay, so
Mike,
come on.
Thank you, Mike.
Very good. Thank you.
Okay, so
All right.
Ruchi,